Well, we might as well go ahead and get started then. Remember that last time we were starting to develop this really cool picture of how we can take this single processor and share it across a bunch of programs that are running at the same time. And this turns out to be sort of the underpinning of all of the major aspects of our operating systems that we use every day. In fact, part of the background of this, we don't get to talk about it too much, but maybe I'll spend a minute or two talking about it today, is from the 60s and the 70s where a school, a university, instead of having multiple computers per student, which is how we do things now, would have one giant computer for the entire university. Or you'd have a large company and it would have one computer because they were large, they were rare, they were expensive, they required a lot of infrastructure to run properly. And so you'd have that computer running one program, and then the program would turn around and decide to talk to a tape system or to print something. And so you'd have this situation where this computer is now sitting there waiting for a peripheral to complete its task. And you're sitting there not doing computations with this big expensive machine. And so they said, well, what would be even better is if we could figure out when one program is waiting to complete some I.O., switch to another program and let it run and do some things. And if that program stops on some I.O., we should let it wait and turn around and run another program. And so this is where the concept of multitasking came from. Wanting to take this large, expensive computer and maximize its usefulness. Maximize the bang for the buck that they're putting into this big machine. And so it's kind of nice because now that computers are ubiquitous, you could really have like a program running per processor or whatever, and it would be wasteful, but nobody would really care because we have so many processors now. But a lot of this stuff came out of the fact that it used to be a lot more difficult to get access to a computer, and you'd want to use it as maximally as possible. So that's where some of these things spring from. We talk about that a lot more in the beginning of 124. It's a pretty interesting topic. But we have this control process, managing other processes. Remember, this was our operating system kernel. It was responsible for managing the hardware on behalf of other computer programs that are running. And it does have very similar process abstraction as the other processes. We have a machine context that we can save for that thing and everything. So the controller is the thing that performs context switches. We figure out a way of stopping the currently running program with all of its context. We call it a process. We save that context somewhere else in the computer, and then we copy some other program's context to the processor and resume running it. Okay? So that's how we do this kind of thing. We also talked about operating mode. So this was just how do we actually enforce the difference. It turns out you have to enforce these things in hardware. You can't really emulate them in software. We used to have kind of a fun assignment 8 where we provided a mechanism by which you could try to do it in software. And you, the student's job, was to actually find a way to compromise the security of the system. And people had a lot of fun. We always saw a lot of interesting ways to compromise the security of the system. But students walked away saying, I didn't really learn very much about virtual memory in this, so that's why we have the current assignment that we do. But you find out very quickly that this stuff has to be enforced by hardware. Otherwise, if it's enforced by software, you can always work around it. There's always a way. So applications run in normal mode, and the control process runs in kernel mode, and it can actually do everything that the processor is capable of doing. More or less. This is an abstraction of what happens for reals because we haven't talked about hypervisors or system management software or anything like that, which even goes beyond what we're talking about here. So yeah, operating systems, rah. Now we had logical control flow in a process. That was basically you write a program and it does computations, and the sequence of computations that it does, it's looping, it's branching, it's function calls, all of that stuff is the logical control flow of the program. Okay? And then exceptional control flow is when we have to interrupt that logical control flow for some reason. And so we talked about the various categories of exceptional control flow that we might have. Hardware might say, I need attention. Software may say, I need help. Software may unintentionally do something that the operating system needs to get involved in. That's a fault. And the hardware may just freak out. Okay, so we have these different circumstances that can occur along the way. And with this, we suddenly start being able to implement real operating system features, like being able to interrupt the currently running program. We give it a certain amount of time. When that time runs out, interrupt goes off, the operating system gets informed, and it copies the program's context off of the processor and copies some other program's context onto the processor so that it can now have a go. Okay? And we have a lot of other things that we can do with these mechanisms as well, which we're going to explore a lot in the next few weeks. Okay, so this was basically where we left off last time. Are there any questions? Any thoughts or questions people thought of along the way, considering all of these things? Okay, so this is basically where we left off. We started talking also about how you would actually get into the kernel, and we introduced the mechanism called a software exception, or the int instruction in x86. We're going to spend a little bit more time talking about that, but the most important detail is you can't just get straight into the OS kernel however you wish. That has to be controlled very carefully so that you don't accidentally expose information or functionality that the application shouldn't have access to. This kind of thing, every once in a while it crops up. You see a security flaw in an operating system implementation. You realize, oh, this is really important to get correct. So you have to trap into the kernel somehow. And I hope you understand the notion behind this term trap. It's like there's a trap door. Somebody engineered a trap door into the operating system kernel. And it's like the one. You can go through it, and there's guards standing around it so that you can't do anything naughty. But you have this one engineered way of getting into the operating system. The way that you can do this on x86 is to use the int instruction. Now, I'm going to give you a very important detail that has changed. Up until last year was the first year that we started teaching x86 64. Up until that point, we taught IA32 because that was the 32-bit instruction set architecture on x86, and it had its own calling convention, cdecl. And to get into the operating system kernel, you would issue an int with a specific number. It would happen to be hex 80 or decimal 128. That was the way that you would get into the operating system. Once we moved to x86 64, we changed that mechanism because interrupts, it turns out, are really slow. And we'll talk about that some in assignment 6. But I just want to say that up front. Int 80 is still the 32-bit way to get into the operating system kernel. With x86 64, we have another much faster way of doing it. It's like 20% or 25% of the actual time that the int instruction takes to get in. So it's a lot faster. Especially when you think about it, that everything your program is doing is it's either computing or it's going to be interacting with the operating system. So we want that mechanism to be fast. Okay? Okay, so x86 64, each privilege level has its own stack. This has been true since x86 has gotten protected mode execution. So privilege levels have always and probably will forever have their own stacks so that they are isolated from each other very effectively. And so when you're changing protection level, you do have to switch stacks, and that is nice for certain reasons. We talked about some of those things last time, but it does make it hard to pass arguments on the stack because now you have to look at the pointer on your stack to the stack you came from and access the arguments from the stack that you came from. Who would want to ever do that? And so the way that operating systems tend to handle this is you stuff your arguments into registers and then you trap into the kernel. Okay. And again, you have a calling convention. One of those registers will be the operation to perform. Other registers will be, you have this register as the first argument, this register as the second argument, so forth, all the way through the sequence of registers. And then you can pass arguments to the system call. How do you get information back? Well, it's the same way that we return results from a function. One of the registers will be where the return value is stored. Happens that it's in RAX, just like with the x86, AMD x86 64 ABI calling convention. We stuff it into RAX. Alright, so I'm going to show you what it looks like for using int, but just keep in mind this is the 32-bit mechanism, and in assignment 6 you'll see the 64-bit mechanism. It's really straightforward. It's not hard. Okay. So you put the operation perform in RAX. It's some number, and you can imagine that the system call dispatcher has a big switch statement of some kind that says, if it's this number, go to this thing, and if it's this other number, go to this other thing. If it's a number I don't recognize, send back an error message saying I don't know what you're talking about. So it's a very straightforward piece of code. These operations and their numeric IDs varies from operating system to operating system. That's why you can't build something on Windows and run it on a Mac. Or I should say that's one of the reasons, even though they use the same kind of processor. Or build it on a Mac and run it on Linux. The system call numbers are different, and even the operations that are provided are different as well. Okay? So you have to be careful about that kind of thing. Now, I happen to try to choose system calls whose numbers are the same across OSs. Okay? So an example is get PID. What's PID? Well, a PID is the ID of the current running process. The operating system has to have a way of identifying them, and so it gives each one a unique number. And so that's the process ID. So we can call this get PID thing, and that happens to be ID 20. You put that in RAX. You trap into the kernel. The kernel looks at it and says, oh, they want to know their ID. And so it just plops the process ID into RAX, and then IRETs back. That's all it does. Really easy, right? Any questions? So this is the 32-bit way of doing it. There is a 64-bit way, which is much faster. It uses these two instructions called syscall. That's a great name, right? Hey, I'm making a system call. So it's called syscall, and the return is sysret. Okay? And it has a much simpler mechanism for getting into the kernel. So you'll get to read about that in assignment 6. There also turns out that there's another pair of instructions called sysenter and sysleave. That's kind of what happened when AMD and Intel developed their own 64-bit instruction sets. They kind of came up with different ideas, but it's all kind of merged now into a single instruction set architecture. Okay, yeah, so you normally don't invoke system calls using assembly code. Why would anybody do that? The standard library has functions that wrap all of these operations, and those are the things that you should use. You'll get one opportunity to do it in assignment 6, and that's basically to see that it is a thing and that you can use it. But after that, even if you were to ever do these kinds of things on your own, the worst you would do is use the syscall function, which wraps the system call mechanism. But then really what you're going to do is call read, call write, call get PID, call fork, call exit, those kinds of operations to do your things. Okay? Yeah, so this is what I was saying. It was really wild because people were starting to get real operating systems because, you know, once you get protected mode execution, you can start building operating systems you're not ashamed of, and you have to trap into the kernel. And so people were writing programs that trap into the kernel to do things, and they suddenly discovered that moving from Pentium 3 to Pentium 4, where you switch stacks and you do all these privilege level checks and all of that kind of stuff, suddenly it was insanely slow compared to how it used to be. So programs were just all getting a lot slower because they were all interacting with the kernel. And so they said, we need to come up with a better way of doing this. Okay? So that's why we have these other operations to enter into the kernel. And when you see the difference, like assignment 6, it's got a little table for you just to illustrate. These are the things that happen when you do an int to get into the kernel, and here are the things that sysenter does or syscall does. And it's like, wow, that's so much faster. No wonder it's so much faster. Okay. All right, yeah, we'll talk about this more when we talk, although it's funny because when we start talking about virtual memory and this mechanism, you'll start to realize that even that has changed just in the last 6 months because of the various speculative execution exploits that people have devised. So I'll try to tell you about that when we get there. The only constant thing in computer systems is change. It's really frustrating. It's hard to keep up with. Okay, so here's some system calls. Open, close for file I/O. Read and write for reading and writing data to a file. Lseek if you want to go to a particular position in a file. Remember, the file system is part of the facilities that the operating system provides, because nobody wants to talk to a disk controller unless they absolutely have to. And not only that, but you've got the hard disk, you've got the solid state drive, you've got the CD-ROM, you've got the flash memory, you've got so many other kinds of storage media. Who wants to talk to each one of those kinds of devices? So the OS provides a nice simple API. Directory operations: make a directory, change to a directory, remove a directory. Unlink is fun because that's actually the delete operation in the file system. Unix makes a distinction between the directory entry, which points to the file data, and the file data itself. And so you create links, hard links or symbolic links to a particular file's data, and then unlink is just removing that directory entry. When the number of links goes to 0, then the file data is reclaimed. It's a really straightforward mechanism. And then you have various process operations as well. I love Unix's process model. It's simple enough. It's like the Python of process abstractions. You want to make a new process? You fork. Now you have two processes running the exact same program. One's a parent, one's the child, so they can start to diverge in their behavior. If you want to run a program, then you can exec, and so that'll start running a new program in the current process's context. Or you can think of it as just resetting the context so that now you're reloading the context from a new program, binary. Exit to terminate a process, kill to send another process a signal. It kind of is an unfortunate name, kill, right? Because there's a lot of things you can do besides killing a process when you send it a signal. But it turns out the signal is used for registering a signal handler, so that's why we call it kill, I guess. And then you have wait, where you are waiting on another process to change its state. So these are just a few. Okay. Now, what's the common theme? I say common theme across many system calls. What's a common theme across many of these system calls? They talk to ... fill in the blank. Slow storage devices, right? Everybody see that? I'm reading a file. How long does that take? Well, tens of millions of clocks. Makes me sad. Maybe I'm really happy I have a solid-state drive and it's hundreds of thousands of clocks. Okay? You have your directory operations. Those obviously interact with the disk. So, since we have this circumstance, we have interactions with other processes. We have interactions with slow devices. Guess what frequently happens when you make a system call and interact with these devices? Your process is now stuck waiting. So why don't we switch to another process and let it have a go? Okay? So we frequently see context switches performed when programs make system calls. In fact, this is a really important detail because when we had cooperative multitasking, remember we talked briefly about how cooperative multitasking is nice. It's simple. You can implement it in an assignment. Like you guys are going to actually get to implement cooperative multitasking in assignment 6. And it works pretty well because every time a program makes a system call, you can switch away from it. And so that's why you can build an operating system with just cooperative multitasking that doesn't suck too bad. It's only when you have a compute-intensive program that hogs the processor that cooperative multitasking starts to show its weaknesses. Or a program that doesn't give back the processor. It doesn't make any system calls and it sits in a tight loop or something like that. And now the whole system is hung. Okay? So context switches when system calls are made extremely common. And I'm going to mention this again because a lot of times on the final I like to ask questions about these kinds of things. This is a conceptual approach about how operating systems are implemented since we have operations that take a long time because they involve I/O. Context switches are really common to do at that point. Okay? So you have two programs running. They're running concurrently. Remember, that just means they have overlapping logical control flows. So program A is currently on the CPU. Program B is suspended somehow, and program A decides to read. Now it's waiting. Let's assume that the data is not in any operating system buffer and it's not anywhere else that we can get it really quickly. So now we're going to be waiting. Program A can't do anything anymore. So what we need to do, remember that program A is going to ask the kernel to do this on its behalf. So it traps into the kernel. It says to the kernel, I'd really love to read this data. The kernel says, sure, let me get that set up for you. But now everybody's going to be waiting. So the kernel can go do other things in the meantime. Okay? Now the question is, how do we actually set this up to happen in the background? And again, anybody who's done embedded systems implementation, I hope you've gotten to experience the joy of dynamic memory access, where you can have a peripheral interact with memory directly. Okay? We'd like to have peripherals that are intelligent enough that when the processor is doing one thing, the I/O subsystem or the peripherals can go do something else so that we don't have to have supervision from the processor all the time. It would be such a drag. So this tends to be a common computer layout if we're going to talk. I mean, this is a very high level, hand-wavy schematic view of how the system looks. You have the processor. Remember, all the caches are sitting on the processor on the CPU side of that bridge. Then you have a bridge that knows how to talk either to memory or to a peripheral bus. Now remember, we looked at that memory mountain thing. We talked about that program with the measurements, and we saw that it could transfer like 6 gigs of memory a second. That's super fast. Certainly a lot faster than most peripherals. And so you can imagine that the memory bus is going to be engineered to be much faster and probably less flexible than the I/O bus, which has to talk to a lot of different things. Okay? And then you have the I/O bus, and that may have things like USB controllers hanging off of them, where the USB controller sits on a bus, and then it's got other devices that it's talking to and saying, who are you? What are you? And the devices can say, this is what I am, and so forth. That whole discoverability thing, it's pretty powerful. We'll talk about that more in 124. But you can see here that we have all of these things tied together with these various buses. So the system and memory buses are fast, and the I/O bus is going to be slower, but it's going to support things like discoverability. So that bus is really smart, okay, but it happens to be a lot slower. Now, you have the CPU doing its thing. Program issues instructions, or let's say even the kernel issues instructions. And the instruction happens to be a read or a write, so it hits memory. Or you have port operations, input on a port, output on a port, and so you're interacting with things on the I/O bus. Okay, no problemo. We can definitely write programs to do that. But we have the issue that if the CPU had to be involved with every byte or every word being moved from the disk controller to memory, just so that we could load some data off the disk, then that's a slow way of engineering that system. We really would like to not have the CPU involved in this process because the CPU is there to do computations. We'd like to get the data into memory, do computations, and then, I don't know, display it to the screen or save it back to the disk or whatever the user wants. Okay? So we need a better way to do this. So some of these buses, and obviously you can imagine what parts of the system have to be clever to support this kind of an interaction, but some buses support peripherals that know how to drive the bus. They know how to take control of the bus and do things. Okay. And so we could have a situation where the CPU tells the disk controller, here's what I want, hey disk controller, this is what I'd like you to do for me. I'd like you to load this logical block or this collection of logical blocks, and I'd like you to store them at this set of memory addresses for me. Okay? And so the disk controller waits, it goes ahead and starts the access. It slews the disk arm where it's got to be so that it's in the right cylinder, and then the sectors come around and all that data gets sucked off the disk. And now the disk controller has the data. Now it can go ahead and move that data directly to memory without having to involve the processor. How cool is this? Because now the processor is able to do its own thing. So yes, this is called direct memory access, and that specific kind of an interaction is called a DMA transfer, a DMA read or a DMA write, depending on the direction that it's going. Yes?
Are there like protections in place, or can anything on a DMA transfer anything in main memory systems that are involved?
That's a really good question, what protections are involved. I'm not sure that there are many protections involved, because the memory management unit, which we have not yet talked about, but that's the thing that actually enforces permissions for memory accesses, is living on the processor. So it's not even in the I/O bridge where this interaction is going to be going through. Okay? So this is kind of an interesting question. Do you trust the hardware that's plugged into your computer? And the answer is usually yes. But it's certainly possible that your hardware could be doing something nefarious. That certainly has been done in the past. But it kind of does also present the reality that if you have access to the computer hardware, you own the computer. You can do whatever you want with it. And so any kind of security measures become extremely difficult to maintain if someone, a malicious attacker actually has access to the compute hardware. But yeah, in this case, the component that actually does memory permission checking and enforcement is on the CPU side of that I/O bridge. So yeah, DMA transfers can do whatever they want, basically. Any other questions? All right, so this is very fast and very fun. Now, you may actually ask yourself a question. We're going to talk about this a little bit, but I want to mention it to you now because you can see the red arrow, right? Something talking to main memory. Now you might say to yourself, is this going to interfere with the processor interacting with main memory? Well, maybe. If the processor needs to load a block from main memory, then yes, those two things have to share the memory bus. But if the program is written with good locality, then that means it should actually be reading and writing from its caches, which live on the CPU side of the I/O bridge. And so the CPU won't even care. The CPU is going to be just doing its thing if the program is written well. And then these kinds of interactions between peripherals and the memory will be perfectly fine. They won't be hindered by that. And so you can see yet another benefit of hardware caching is it allows us to do these DMA transfers without the different subsystems interfering with each other very much. Everybody got that? Another really powerful benefit of hardware caching. Okay, yay for CPUs. So yeah, step one, CPU tells the controller to read data, and then the controller does its thing. Now, how does it know when it's done? This is kind of the important detail here. The disk controller does its thing. Now, at the end of it, the disk controller needs to say to the processor, I need attention because the data that you asked to be transferred is now transferred. Okay? So you have a hardware interrupt that's fired. And it tends to be, there's a special part of the processor, at least on x86, called the APIC, the Advanced Programmable Interrupt Controller. And one of the things the OS does is it says, hey, disk controller, when you need to talk to me, here's your interrupt number. And then the disk controller says, aye, aye, Captain, and then, that's what happens. So that interrupt will get triggered. The operating system will go and look and say, the disk controller finished the DMA transfer, so now I can go, do the next step, whatever. I can go back to process A because its data is ready. Okay? So now the OS can do other things while peripherals perform the slow operations. Okay? So this is really cool. This is really powerful. Now, the next slide or two sort of tell you how important DMA transfers are. It turns out that they're extremely important for building high-performance computing systems. Okay? Anytime you want to be able to do fast graphics, fast sound playing, be able to play high-fidelity sound on your computer, you want to be able to do fast I/O with either network cards or disk controllers and so forth. All of this, the only way you can make it fast is by doing these DMA transfers so that the CPU can go orchestrate and engineer other things while the peripheral interaction is occurring. Okay? Now you can imagine that the I/O bus, this peripheral bus, if it's going to support DMA transfers, then it has to support the ability for different things on the bus to say, I want to be in charge of the bus. And so typically there's some arbitration that needs to occur if two things decide they want to talk on the bus at the same time. Sometimes it's a priority-based thing. Sometimes it's a round-robin type thing. It's not your turn. You have to wait for the other peripheral on the bus to do its thing, and then you can have the bus. Okay? So you have all of this engineering that has to go into it. The PCI bus is a really sophisticated piece of engineering. That's one of the most common peripheral buses used these days. Okay? And so while the DMA transfer takes place, the CPU access to memory is slower, right? Because we do have like a limited amount of bandwidth and it is being used by something else. But as long as we're staying in our caches, we don't care. We won't even see it. Okay? So that's the big benefit of good locality. All right? Let's see. What else do I say here? Yeah, so this is an interesting question. Cache coherence. Because notice that you still have the hardware caches on the CPU side, and you got memory on the memory side of the I/O bridge, and then you have peripherals now interacting with memory. So it's possible that you now have hardware caches with invalid data. Okay? So how do you deal with this? Well, typically you deal with this by carefully designing how you interact with the system. Okay? You could either do the hard thing, which is have the processor listen to what happens on the I/O bridge. Okay? That's if you want to make a really automated system where you don't have to think hardly at all and everything just happens magically, perfectly fine. Tends to be that if you can solve these kinds of problems with careful engineering, then, and it's not that much harder, then we go ahead and just solve it with engineering. The other option is that the OS can just say, I know this address range is going to be used for DMA transfers. So I am going to flush these cache areas, this address range. I'll go ahead and invalidate those cache lines and then read, and I know I'll be seeing the data that was transferred by the DMA transfer. And if you think about it, since the processor is informed when the transfer is complete, like somebody read data from a peripheral into memory, it knows that any cached data would be invalid. So it can go ahead and invalidate those address ranges and then do the reads, and it knows it'll see the transferred data. Okay? So you have an easy solution, and you have a solution that's more challenging to implement in hardware. Yeah?
By invalidating the cache, since that happens on hardware, do you mean that the OS would remap that region?
Yeah, address range mapping will be happening, but for other reasons, because a lot of times these peripherals can only access a specific range of addresses. So you may have the processor, which I've been blathering on about for the whole term, 48 bits of address, so you can access 256 terabytes. That doesn't mean that the disk controller knows how to talk to 256 terabytes. So it may know how to talk to 128 megabytes or something like that. And there's actually ways of mapping that address range as well. And so the operating system will be involved in determining where each of these things does its DMA transfers. So it knows the memory map that's used for the hardware. But that's a separate matter from whether or not things are cached. It turns out that those two things can be controlled separately. Yeah. All right, anything else? Okay. So we had these two programs running concurrently, although program A is the one that's actually doing stuff right now. It traps into the kernel saying, I want to read. And so now we know what the kernel does. It sets up a DMA transfer on behalf of program A, probably using memory that program A can't access right now because it's going to be using something that the disk controller can access. Sets it up, and then it knows that program A can't do anything. So since it can't do anything, it can go ahead and switch to another program, let it run for a while. So now program B is running, program A is suspended. And when the ding goes off at the end, because the disk controller signaled the processor using an interrupt, then the kernel can make sure that data is somehow available to program A. The way that these read and write operations work is with read, you pass in a pointer to a buffer. And you say, this is where I want you to put my data when it's read. And so the last step that the kernel has to do when it's getting ready to go back to program A is say, okay, let me put the data where you wanted it. And then program A will get back from the system call, and lo and behold, like magic, there's the data. Okay. Handles the interrupt, and then it could context switch back to program A. Questions? I'll point out one detail here which is really important. It will become more important as we go into how this stuff is implemented. You can already see that programs, as they're running, can be in different states. So program A is running. It sits on the CPU. It's doing stuff. Program B, it says it's suspended, but it also, furthermore, we know could run if it had a CPU. Everybody see that? Because when program A decides to do something that takes a lot of time, the processor says, okay, well, not the processor, the operating system says, okay, let's switch to program B. Now, program A is suspended, but it's not just suspended, it's blocked on an I/O operation. So there's no point in switching back to program A until the I/O operation completes. Okay? So you see that processes can be in various states, and the operating system kernel keeps track of this so that it can say, all right, so-and-so is getting off the processor. Who can I pick to put on the processor that would actually make use of it? Or who is blocked on some I/O operation, so there's no point in giving them a processor. Okay, so these are the kinds of things. I always say that operating systems are just glorified bookkeepers. Okay, and they kind of really are. They just keep track of a lot of little details. The only thing that makes them really difficult to write is A, they talk to hardware directly, so good luck debugging them. And B, a lot of stuff happens at the same time. You try to get maximal concurrency, and that's difficult to reason about for us. So those are the things that make operating system implementation difficult. Other than that, they're just bookkeepers. Okay, so you can start to see hopefully how the operating system has some really powerful facilities that it takes care of for us. And so we can use traps to get into the OS, to have the OS do things on our behalf. And by using things like direct memory access, we can go do other things while a program is stuck on a slow I/O operation. And so, and again, this is the giant, most important takeaway that you should always think about when Donnie asks systems questions on the final. System calls are a great opportunity to do context switches, because almost invariably they will involve a lot of waiting in the completion of that system call. What better time to switch away from the process and let another process run? Okay, questions? Good. Let's see. So exceptional control flow. What an amazing invention. Now, here's the thing. So far, the way we've been talking about this is only available to the OS. You know, the OS is the thing that gets the interrupts. Remember that whole interrupt dispatch table thing it's got to set up, and here's my handler, and the handler does junk. And it turns out to be pretty complicated. Who wants to deal with all of that junk? We'd like to have some way of doing this in user space programs as well. And here are a few simple examples. Let's say that I'd like to also receive a timer interrupt for some reason. Okay? I can't talk to the hardware timer myself because the OS has that under control. It uses it for context switching so that I will eventually get another time slice on the CPU. So we have to ask the OS to do it for us. Here's another one, clean shutdown operations. Let's say that I segfault, but I'd love my program to clean up after itself. Now, so far you don't care about that. Your program segfaults, it's not like your computer becomes unusable, unless you have a really poorly written OS or a really strange program. Okay? But there are programs where maybe I had a bunch of open files and I would like to clean all those files up properly. So you'd like to do something when the segfault occurs, or an illegal instruction execution, or something like that. So these are all important things that need to happen. So it'd be nice to be able to have a signal when that occurs. Or you'd like to be able to send a message to another process to tell it to do something. The typical example, if anybody's done any kind of system management, in a Linux system or a UNIX system would be, I want to send a signal to this process to tell it to reload its configuration so I don't have to wait for it to shut down and restart. Okay? Very common approach, used with web servers all the time. So the way that that is exposed into user mode programs is through a mechanism called signals and signal handling. Okay? This is basically exactly hardware exception handling, but mapped into a user mode application. Okay? Here is a small sample. I mean, that may look like a lot, but it turns out to be a relatively small sampling of the kinds of signals that programs are able to receive from the operating system. So let me see some fun ones. 2, SIGINT. That's one that we all use all the time. Control-C'ing a program to make it stop. SIGQUIT. Maybe you didn't know, but you could also hit Control \, and that would stop the program. And it turns out that it uses a different signal. You have SIGIL. If you decide to execute an instruction and it turns out that the processor doesn't know what you're talking about, it'll fire a particular hardware interrupt that gets mapped into an illegal instruction signal. Okay, and so forth. You can go, you have SIGSEGV, that's your segmentation fault. You tried to access memory and it was wrong. And then you have SIGALARM, which is the timer interrupt goes off. Now notice the default action. This is what UNIX says, this is what's going to happen by default when any of these signals happens. What's the default usually? Terminate the program. We're just going to shut it down. That's why you can Control-C and it shuts down your program, or you Control / and it'll shut down your program. Okay? But it turns out that you can register a signal handler for most of these and do something else. So you can have a non-default behavior and actually respond to that signal. If you look at these signals, like I was saying, many of these things are signaled by the compute hardware. They're not actually software circumstances that occur. SIGALARM, SIGFPE, I saw a few people running into that on the cache simulator probably because they were trying to do modulo by 0, and so you get a divide by 0 interrupt that occurs. These things are mapped directly by the kernel to the process that did it with one of these signals. Okay? Then you have other ones which are routed through the kernel, because remember that the kernel is a trusted intermediary between processes. So one process wants to terminate another process. You hit Control-C in your command shell. Your command shell makes sure that that Control-C makes it to your program. Okay? Same thing with Control-Z. Does anybody do Control-Z to put their programs in the background or just to suspend them for a while? A few of you do. Okay? Very powerful thing. I wish everybody knew how to do this, because sometimes you're running a very compute-intensive program and then you need to stop it for some reason. You can just hit Control-Z. Send it a T-stop signal. And that tells the operating system, stop scheduling this process on the processor. And then you can send it another signal, SIGCONT, that tells it to continue. So it tells it to resume scheduling it on the processor. Okay? So these are interactions between processes that aren't from hardware to a process, they're from a process to a process. Okay? So the kernel will receive signals, let's say, remember we're using this term loosely, it will receive hardware interrupts from hardware, or it will receive signals from other processes, and it will route them to processes on behalf of other processes. Okay? So this is the way that the kernel is operating. Again, illustrating this notion that the OS is a mediator between the compute hardware and the applications. All right? So this is the idea behind signals. Now, you use this function called signal. I mentioned that kill is called kill, whereas you'd like it to be called signal because that would make more sense. But it turns out that we have another function called signal, which actually allows you to register a signal handler. Okay? It takes a function pointer as an argument. Notice it takes a pointer to a function that takes an int and returns nothing. Okay? Thus we declare it like I have on the slide. Typedef void and then in parentheses star handler t, and it takes an int. And that's the signal type that was received. Every signal type has a different number associated with it. Okay? And so this is a system call that you use to tell the OS when this signal occurs, I'd like you to call this function on my behalf. Okay, so that's what happens. You can also pass a couple of special values, sig-igen, which says to ignore the signal, which means don't do the default behavior. So remember the default behavior was frequently to terminate. Well, you can make it so that you just ignore the signal instead. You could say, I don't care about illegal instructions. I don't care about seg faults. Sig-igen. There you go. Okay? Or sig-dfl to use the default handler. There is one signal you cannot ignore. It's sig-kill. Sig-kill is the escape hatch for the operating system so that you can always have a way of forcibly terminating a process. Okay? This is for circumstances where processes have decided to ignore everything and are dead to the world and are otherwise consuming lots of resources. So you can always send it a sig-kill to stop it. Okay? I don't know. Has anybody here had to kill -9 anything? Show of hands, a few people again. So guess what? 9 is the numeric value that's used for sig-kill. And so when you kill -9, you're saying, OS, I need you to forcibly terminate this process with prejudice because it cannot run any longer. And typically you do that because other signals like sig-term, sig-quit are being ignored. Okay, here's a nice simple example, program that catches Control-C. So notice our main function registers a signal handler, it handles sigint, and then it sits in an infinite loop because why not? That's the purpose of the program, is to just look at our signal handler. And so all the signal handler does is print out that it caught the signal. So when we run this from the console, I happen to call mine noint, but you run it and it outputs nothing, so you hit Control-C and it says, I caught a signal. Then it says nothing again, and then you hit Control-C again, and it says, I got a signal. Isn't that exciting? This is like the world's most amazing program. Then you hit Control \, and that happens to not send a sigint. That sends a sig-quit. And so the program stops because the default behavior is to terminate the program. Okay? So that's a simple example of signal handling. Okay? So simple example. Now, the reason why we have this pause call in here is because the whole purpose of the program is to illustrate signal handling, signal delivery. And so we'd like it to not just say while one, semicolon, right? I don't know if any of you have written a program that just does while one, semicolon, or something in that vein, but you probably are aware that one of the first things that will happen is your fans will all start turning on because your computer's sitting there just spinning in a circle doing nothing. Okay? Very quickly doing nothing. So pause is like a nice passive way of being in a loop. Pause basically says, I want to go to sleep until something interesting happens. It doesn't say what specifically happens that's interesting. It just says, I want to go to sleep or I want to be suspended until anything interesting happens. Okay? Oh yeah, so I don't actually talk about that here. But for example, pause will return once a signal's been delivered. Okay? So pause is a nice way of passively waiting for something interesting to happen. Okay? Happens to be another system call. Okay, let's see. Yeah, so this is kind of an interesting little detail. You'll notice it handles sigint, just prints out a message and then it returns. The question is, where does it return to? Well, whatever point the program was interrupted at, this is exactly like exceptional control flow at the hardware level. It's going to be inside that while one loop somewhere. And then when handle sigint returns, it's going to go back to whatever point that loop was interrupted at. That's basically all there is to it. It's really straightforward. Now here's another one. Let's say that we want to actually get a 1 second timer. Now you'll notice that this program is a little bit, first of all, it's not a very nice program because it taunts the user. But the other part of it that you notice is that if you want to get a signal every second, then what you have to do is say, give me a signal in a second. And then when you get it, you have to say, okay, give me another signal in a second. And then when you get that one, you have to say, give me another signal in a second. So you kind of have to sit in this loop of continually asking for another signal. So that's the whole idea behind alarm 1. So you can see we register our signal handlers at the start of main. 1 for sigint to taunt the user, and 1 to say hello, because we're a very friendly taunting program. And so we alarm 1, and that will ask for a sig alarm in 1 second. And then we sit in our infinite loop. Okay, and then to handle sig alarm, it prints hello, and then it registers another request to get another sig alarm. And so you can see that the loop here that causes periodic sig alarms is coded up in the signal handler. It's a little bit different than you may be used to. Okay. Any questions? All right. So we do have this interesting thing that you start to notice is that we have these two signal handlers, and it is conceivable that one could interrupt the other one. So sig alarm is running, it's printing out hello, and then somebody's hitting Control C, they're mashing Control C because they're angry at the program, and you've got, haha, can't kill me being printed out at the same time. So these two printfs could overlap. So it's conceivable that we could have their output interleaved in some way. And so this is one of the things that you start to notice about signal handlers. Since they can interrupt anything, including other signal handlers of different types, we have to think carefully about how we implement them. Okay, like I mentioned, your printf has global state, so it's possible that these two functions could overlap in their execution, and you'd get weird, spurious output. Since signal handlers can interrupt anything, including other function calls, we have to make sure that signal handlers are written carefully so that they don't destroy the program's brain. And that's basically all it comes down to. We need functions that are reentrant, which basically means I can have multiple overlapping invocations of the same function without the function becoming completely broken. Typically, that means that we have no global state that's being managed. Number one culprit, number one issue that you can run into with signal handlers is malloc. Does malloc have global state? Yes, most definitely. You all know what it does now, because you got to start somewhere in your heap and start hunting for a place to get a block, and then maybe you need to split a block, and it's just mayhem all by itself. You all, I'm sure, either love it or hate it. But then you have a signal handler happen in the middle of that, and somebody decides to malloc or free. And now you've got another invocation of the same function that is expecting to be the sole invocation, and it's trying to mutate the same shared state. Now you get into all kinds of disastrous results. Okay? Everybody see this? So we have to be very careful about how we implement signal handlers. They have to be very carefully implemented to only use reentrant functions. Are there any questions? All right, we will leave it off here. We'll pick this up next time and continue this discussion.